Hi y'all, I'm in the middle of building a custom Macropad. Here is my first prototype, which has 12 keys and a couple of rotary encoders. If you look at it from the bottom, it is all hand-wired and has an RP2040 microcontroller to make everything work. Actually, this configuration is similar to something like this that you can get easily from places like AliExpress. I have been using this one for some time for video editing, but the problem with this was that it runs a custom firmware that is not open source, and the software to program it was for Windows only. This was a bit of a problem. With a Macropad, you might want to remap the keys all the time, but as a Mac user, bringing it to a Windows PC every time was a bit tedious. Especially because its software was like a half-baked thing, which works but hardly fantastic. I knew there are great open source keyboard solutions such as QMK and its offsprings. They could be used across platforms and often comes with graphical UI. There are also many commercial keyboards and Macropads that support these, but I couldn't find one yet that's suitable for me at an affordable price. Also, I thought it's better to place diodes between the rows so that I could separate buttons according to different category or usage. So, building a custom Macropad was on my bucket list for a long time, and finally I decided to work on it. It was not an easy road though. To build a custom keyboard, you need at least some knowledge and experience about electronics and software development. And for those, you have to learn to use software tools such as KiCAD, which is for circuit design, and terminal commands and programming languages for building firmwares, and GitHub for project management. And the list goes on and on. As I'm no expert in any of these subjects, I only have been circling around, trying and giving up until now. But last October, I have been contacted by PCBWay, who offered to help me with their on-demand PCB services. With a custom PCB, this project will be at another level totally, so I said why not? Currently, I have ordered and I'm waiting for my second and hopefully the final prototype board from PCBWay, and in this video I would like to show you my design process. So here are what I used for this project. An RP2040 microcontroller. I chose this variant called RP2040 because of its tiny footprint. And these are called Kailh Choc V2 switches. I wanted a small and minimal design, so I wanted low profile switches. And this one from Kailh is great because you can use the same keycaps for full-sized switches. And this is an EC11 encoder with 12mm height. Finally, these are 1N4148 diodes that has to be connected to each switch, like you see in my previous prototype. With these components, the circuit is going to be designed in KiCAD 9. But first, I installed a library for building a keyboard. One I used is called Scottokeebs from Joe Scotto, and here's his GitHub. He also keeps one of the best YouTube video channel on keyboard making, so definitely check it out. To use this library, I downloaded Scottokeebs Github project and copied only the folder named Scotto KiCAD under extras to my KiCAD folder. After that, I opened the KiCAD and set up the path to the library. You have to set the path in these three categories that appear under Preferences, which are Configure Path, Manage Symbol Libraries, and Manage Footprint Libraries. Now we can actually start the schematics. Press A to find a symbol to place. And we type Scotto and the switch. And we have the placeholder for key switches. In the same way, I placed a diode. Now for each symbols, we have to assign an actual component's footprint. And I copied them and linked them as a matrix. To connect them with wire, you use this wire tool. Now these are going to be column 0 to column 3, and these are going to be rows 0 to rows 2. So I'm going to place tags for them. You can rotate them by pressing R and copy them for each columns and rows. Now let's add rotary encoders. Because we are going to use the rotary encoders with switches, so I selected this one. For rotary encoders, the center pin named C has to be connected to the ground, so we are going to connect them like so. The switch portion of the rotary encoders needs the same diode, and they are linked as a separate row. And I'm going to wire and label them as row 3. Also, I'm going to place labels on the encoder portion, and they all have to be labeled separately. So I forgot to connect one of the switch pins. Just connect them to one of the columns. So I think that's it for the switch metrics. Now I'm going to assign the footprint for rotary encoder. So for the rotary encoders, you might want to choose the footprint from Scottokeebs library. But the problem is that when you go to the 3D viewer, these 3 pins have to go to these 3 pads. So what I do is to open footprint editor, find the footprint that we need to edit, and go to the 3D models. Now here, you can rotate it to any direction. So let's try 90 instead of minus 90. And I think that's about it. And lastly, I'm going to add the microcontroller. Now what you have to do is to use these pins to be connected to all the labels here. So I just copy them, rotate them around, and put each of them to any of the pins on the RP24A0. And this is about everything we need as far as the schematic goes. And this placement on the RP24A0 is going to change a lot as we continue with the PCB design. So let's move on. Now I'm going to show you how PCB design works. It begins with pressing this button to bring all components and connections from the previous schematics. Put them down somewhere and you can start placing the components. For this work, I made a series of grids based on the size of normal keyboard buttons, which is 19 millimeters square. Here's 19. And I also defined 9.5, 4.75, and so on. And these are like half of the previous one. This one is half of 19. This one, quarter of 19. This, 1/8 of 19. Now when moving a component, your cursor will snap to the nearest pad or center point. For example, now the cursor is snapping to the center point, but if you start moving with your cursor over here, then the cursor is snapping to the pad. Diodes are placed in between the switches so that they can hide under the keycaps of the switches on the left and right. Now if you press this button, you can see the board in 3D, and I want to place the microcontroller mounted underneath on this side. So what I do is to change the side. With components in place, I'll lay down the tracks. Point your cursor near a pad and press X and connect it to the next pad. While connecting the track, you can press page down and page up to put it either on the back side or on the front side. The trick is to optimize the network and find out the most efficient pattern. For example, if you want to connect these two pads between S8 and S12, you might want to do it like this, but it has to make a curve to avoid the hole. So what I do instead is to unconnect all the tracks and then rotate each of them. With that, now you can see that these two pads can be connected in a straight route. Also, if you look at these switches on the right, it might be better to place the diode like that so that the diode does not protrude to the right side. Now I'm facing a problem here. It's making a very long, inefficient curves. So maybe it's better to move this connection to one of these pins. Then the connection will become more efficient. So how I do that? Go back to the schematic. And right now, row 2 is connected to the pin number 12. So I'm going to move it to this side. After that, you always have to press the update button again. Now, as you can see, you have a better connection if you compare it against the previous one. So optimizing the track pattern is going and coming back and forth between the schematics and the PCB design to modify the placement of components as well as routing. So I think I have connected everything except for the ground pin here. And I have intentionally left it out because I'm going to cover the whole surface and tie it to the ground. Now if you press B, the whole area is being covered, and you can see that the plane is connected to the microcontroller's ground, which is connected to the both ground pins on the encoders. And then after that, you draw a rectangular boundary, which is going to serve as the physical cutting line. Hit B again to redo the surface. And if you look at the 3D, now you have a full PCB. Now here's my final version after so many updates. Most obviously, you can see these silk screen prints. By the way, this button allows you to view only the chosen layer. Choose the front silk screen or back silk screen layer, and anything you draw here with these tools over here will appear as the printed items. I have also added my logo and QR code for my YouTube channel, which were originally in SVG format. You can import them from the file menu, and in the dialog box, choose the file location and scale, and there you go. But be careful, because once in place, these graphics cannot be resized. You can move them around and rotate them whatever you like, but they cannot be resized. Only way to scale it was to erase it and re-import it with a changed scale. Anyway, looking at the front and back copper layers, track patterns, components orientation, and pin assignment on the MCU have all changed a lot. Again, I went back and forth between the schematic and PCB to optimize them. I also added screw holes on each of the corners, which could be drawn on the same layer as the boundary edges. So far, KiCAD was not particularly easy for me to learn, but it had a couple of features that surprised me. One of them was that you can export this 3D view as a step file that could be read in other 3D CAD softwares. Now you can design a housing from it, and let's jump over to Autodesk Fusion and continue with my case design. So here it is, my final case design. It's been built in a number of separate files, so let's break it down. First is the knob. I came up with this shape with aluminum CNC machining in mind. One small feature is that it has an insert inside aluminum shell, which is to be 3D printed. This was to make sure that it could be adapted to any encoder stem shapes. Keycaps are a little more complicated. Each keycap is made up of body and the lettering as individual bodies. Letters are 2 layers deep with half buried in the background. And this is to be also 3D printed at home. These are the results from the design. They are still a bit rough, but when compared against the previous tests, I'm quite satisfied. These final ones were printed top side up with ironing on the surface and were coated with matte finish lacquer spray to kill the shininess and obscure the surface roughness. Back in the Fusion, the keycaps and knobs were imported into the PCB file from KiCAD. Then it was imported into this new design for overall case. With everything from the previous steps, it wasn't very difficult to build up this kind of design, which I think is pretty straightforward. I cut a bit of angle on the bottom to make it look slim and floating. And I added these walls inside the bottom space to support the PCB rigidly. The panel and the knobs will be in CNC aluminum, whereas the bottom in resin print. Along with the PCB, I have ordered them from PCBWay, the sponsor of this project. Okay, here are shipments from them, and here's my experience with PCBWay. Dimensions are spot on, and silk screen is crisp clean. Same for the CNC and 3D prints. Smooth surface with good accuracy. To order a PCB from them, you can do it directly in KiCAD with this plugin. In the PCB editor, if you press the button for PCBWay, the ordering page will open with your design already loaded. In the page, I found these buttons particularly useful, which are linked to in-depth explanation about each process. As a beginner, I chose all the default options except for the PCB color or soldering mask color, and they were just fine. To order CNC parts, I needed to export and attach the step files, and I chose Bit Blast Finish to remove the CNC marks on the surface. Even if this was my first try, everything went quite smooth without any problems. I was quite impressed how my product could have been upgraded so significantly with so much ease. Professional level PCB and accurate aluminum CNC with beautiful finish. These kinds of things are what I just couldn't do at home. So I definitely recommend the PCBWay to anyone who seeks to step up their project without too much hassle. Everything is ready, and it's time for final assembly, starting with soldering of the components. I'll just show you the process without too much talking. With the complete hardware, I built firmwares. I built QMK first, but later ported it to what's called VIO. This is because QMK's graphical interface needs your project to be accepted officially by QMK. In contrast, VIO didn't have that problem, and in fact, it was more adapted to graphical interface with standalone app that allows key remapping on the fly. Moreover, it had better control over keyboard layout, especially for those with rotary encoders. Once flashed with VIO firmware, my keypad was recognized immediately when plugged in, and I could remap a key by selecting it, followed by the output code that you want. For modified keys, you can use this quantum tab to choose the modifier, and after that, in the bottom row, select the key. After all, this was a satisfying and rewarding project for me in many ways. I want to wrap my video here. Thanks for watching and see you in the next project.